Wasabi, you guys. Welcome to part 2. We are still continuing in strategic wildcard integrals, so we're still continuing with this walkthrough. So let's go ahead and dive right in. Alright, so with this integral, so this looks very weird. Maybe I don't want to do integration by parts. There must be a faster way. Well, this is very hard to see, but if I sort of combine like this, if we split it, we get 1 over x minus 1 over x squared dx. If you know, the derivative of this is negative 1 over x squared, right? So because this is e to the x, right, e to the x plus e to the x, and then negative 1 over x squared. This is product rule. This is just product rule. So our answer is really just e to the x over x plus c. And we're done. We don't have to do integration by parts or anything, and this is just product rule. Okay, we have the integral of that thing. This looks like partial fractions? Partial fractions? I don't know if I want to do partial fractions. I genuinely don't want to do partial fractions. So, but this is a type of a famous integral here. It's a very famous integration B problem, where whenever, I probably shouldn't put equal, whenever you have this case, you have just x alone, and then it's just x to the power of n plus 1, right? So whenever you have this, okay, what you do is you do a Caveman trick, which I'll show you. You're gonna factor out x to the power of 4. So you're gonna get it out, right? So you get x times x to the power of 4 is x5. So we divided this by x to the power of 4, and we divided this x to the power of 4, so we'll make it negative 4, right? And now what this is it's a basic u substitution. So let u equal 1 plus x to the power of negative 4. Then du is equal to negative 4 x to the power of negative 5, which this is actually what this is. This is very hard to see, very sneaky, but this is what it is. So okay, so now we have negative 1/4 integral du over u. That's all it is. That's all it is. And now you just straight up go ahead and answer negative 1/4 ln of 1 plus x to the power of negative 4 plus c. And you are done. That's it. A very popular integration B problem here, right? You don't have to do partial fractions. That's disgusting. You can just do the Caveman trick. So this is one of the integrals that you should memorize the process, because this trick comes up a lot. So again, it's whenever you see this type of integral where it's just x alone and then x to the power of n plus 1, or if you see something like xn plus x, then you know this is a Caveman trick. Oh boy. Oh wait, we're not even done. Square. Oh boy. X plus sine of x squared. So, are we actually squaring it? Or is there something that we gotta do? We will square it. we will square it, right? Let's not overcomplicate things. Let's square it and sort of understand what is going on. X squared plus 2x sine of x, and then plus sine square dx. Okay, this is easy, right? This is just x cubed over 3, plug in 0, plug in pi over 2, right? So then we get 1 over 3 pi over 2 cube. Okay. And then we have this integration by parts here. This thing here. Okay. So we'll just, let me use a different color. We'll do integration by parts. So we have negative 2x, not negative. I don't know why I put negative. 2x sine of x, negative 2, and we keep going all the way to 0. Alright. There's negative cosine, negative sine. We're done. It's just this. So our integral is just, I'll just read the positive first, 2 sine of x minus 2x cosine of x. Okay, and we just compute that from 0 to pi over 2. Okay. But what about here? What about sine square? This is going from 0 to pi over 2. This is Wallis product. So we just use Wallis product, pi over 2, because this exponent is an even number. Alright, so pi over 2 times, and then 1, 2. Alright, we're at 2, we stop here. This is just pi over 4. Okay, so now here, well, let's evaluate this. Plugging in 0, it's just everything 0. Pi over 2. Alright, sine pi over 2, that's 1. So this is 2 minus, and then pi over 2 here. Cosine pi over 2 is 0. Okay, cool. So that's no worries. Alright, so then we end up with pi cube over 8 times 3, that's 24. And then we just end up with plus 2, and then plus pi over 4. So this is our answer. Oh, that 4. But yeah, this is our answer. And it's a lot quicker than I thought, surprisingly. Turned out very nice. Okay, what to do now? I want to factor this out because this is bugging me. So let's go ahead and factor that out. Factor square root, and we get 1 plus x. This looks familiar. What should be my u substitution? Let u equal square root of x, because of this du will take care of that bottom root x. That's why I want to let u equal square root of x. And you start to realize this is just inverse tangent. So the answer is just 2 times the inverse tangent of the square root of x. Alright, very simple. Ooh, 1 plus cosine square. If that was a minus, then this would have been super easy, but it's a 1 plus cosine square. And there's no trig identity for that. So, what are we going to do? Huh. Interesting. Right? You'd probably thinking, okay, well maybe we could use a trig identity with cosine square. If you want, but then it's just gonna be like it'll be devastating. It'll be a lot of trig work, and I wanna take the fast route. So I'm gonna do a sneaky trig manipulation. So I'm gonna sort of not really conjugate, but what I'm gonna do is I'm going to multiply secant square on top and bottom. So what I'm doing is I'm converting a sine cosine integral into a secant tangent integral. Okay, so let's try that. Secant square of x, and we get secant square of x plus 1 dx. This can actually help, because we can turn this into tangent square plus 1, and now we can let u equal tangent x so that du can take care of this secant square. Alright, let's do that. So, of course, this secant square turns tangent square plus 1, so we'll end up with du u square plus 2. Alright, cool. So now it's a simple integral. Kind of. It's a kind of a simple integral. You have to do, sort of use a, I wouldn't say standard integral, but it's a different case where you now have a constant here. And so, if you remembered, it's the reciprocal square rooted, so it's 1 over root 2 inverse tangent of u over root 2. In this case, it would be tangent of x over root 2 plus c. And this will be our answer. Okay, we have a bunch of square root of x's. Let's do u equals square root of x. But the thing is, we don't have a du. So because of that, we're just going to have to force u sub. So let's go ahead, u square equals to x, and now 2u du equals dx. So now we have 2u square e to the u du. Alright, that's no problem. E to the u, 2u square minus 4u plus 4. Alright, that's my answer. I just have to substitute u back in. Substitute x, square root of x back in. So, is e to the square root of x. This is 2x minus 4 square root of x plus 4 plus c. And we are done. The square root of the square root of x plus 1. Huh. This looks weird, right? If I try u equal x squared, I don't have a du for this, so we're going to sort of do a different type of force u sub, right? Again, I do this whenever I see a radical, or like, let's say like you see a bunch of composite functions, or some sort, whatever, and then it's all square rooted, right? Whenever I see something like this, I'm gonna let u equal the entire thing. Most of the, well, sometimes, I would say, sometimes, but in most cases, if I'm just kind of left with this, sometimes I let u equal square root of, and then whatever this thing is. So it's going to be pretty much a full-on force u sub. Again, it's one of those things where it's like you have to experience a lot of integrals. It's one of those things where you just have to like memorize a lot of memorize process of a bunch of integrals, and this was one of the famous, I wouldn't say famous, but it's one of those integrals where it just pops up a lot in integration B that I just kind of memorized the process for this one. So here, I wouldn't say let u equal everything because it's reciprocated, so it's not fully a full-on force sub, but we're going to include the radical and then square root of x plus 1. And so that's going to leave us a u here, right? And that's okay because it's just a u. We can split it, whatever is on top, and then integrate, right? But then we have no du here, so we're gonna have to force a u sub by solving for x. So let's solve for x, u squared minus 1, and then we have to square it again, and now we found x. And now we have to derive it. So now this is 2 u squared minus 1, and then chain rule times 2u du equals dx. Okay. And this is actually simplifies very nicely, right? 2 times 2, that's 4. U squared minus 1, then u du. And then remember that in our original problem, we have u at the bottom. This cancels out. So now we just have 4 u squared minus 1. That's all it is. Okay. Well then, we'll go ahead and integrate this. This is just u cubed over 3 minus u. So then this whole answer is 4 over 3. Substitute u back in, which is this thing. Cube minus, and then 4 plus c. And this is your answer. I feel like I should have added this into one of the 10 derivatives that you should have memorized, but it's okay. So it's, in this case, if you remember, I think it was a different integral video, I don't remember, but pretty much the derivative of sine square is equal to sine 2x. And the reason is because, I mean, if you apply chain rule, right, this is the same trig identity, it's the same thing as this. So we're going to use that. So let u equal sine square, right? Then du is going to take care of this sine 2x, and we're just going to be left off with 1 plus 1 over 1 plus u squared. And of course, this is just simply inverse tangent of sine square. And we are done. And that is it. Okay, this is a very tricky one. What on earth do I even do? Right? What do I even do here? Let's see. Integration by parts, but then you would have to integrate sine cosine here, and it's like I don't want to do that, right? I don't want to do that. Is there, let's see, so I don't know what this is. I'm confused of what this is. Okay, so I want to experiment with the derivative, right? Is this a sneaky u substitution that I don't know about? So let's experiment. Let's try u equal ln of tangent x, right? Because this seems kind of easier to experiment with. So then du, if I derive this, I get tangent x secant square x. I'm just going to put the dx at the side for now. So I want to simplify this in terms of sines and cosines. So we have secant square times, well, this is over tangent x, which is the same thing as cotangent x. So it would look like this. Oh, and the c's cancels out. Oh, would you look at that? That's technically what we have. So this is secretly a u substitution. It's just a basic u substitution. Okay, let's go ahead and get into it. Alright, so let u, then we know that du is equal to dx sine of x cosine of x. Alright, then we'll go ahead, this is just u du. This is technically just u. Oh wow, super easy then. So then in that case, this is just, the answer is just half of ln square tangent x plus c. And you're done. And that's it. So very hard to see this. Another thing that you have to get used to is just experimentation. You know, experiment with this derivative. Maybe there's, if I let u equal this, what would the du come out? And you just have to sort of try. Again, practicing a lot of integrals and then memorizing the process of this so that whenever you encounter it, you know exactly what to do. This one also looks very weird. Trig sub? Maybe? Should I do trig sub? I don't know. Those aren't x squares. I mean, you can let x equal tangent square, but then that's gonna, I don't know. That looks nasty, right? I have to deal with d theta and then a bunch of other stuff. This is very weird. So what do you do? So this one's also a little sneaky if you're not very comfortable with algebra. So here, this is just, we could just conjugate it because this is really radical. So we'll go ahead and conjugate this. Let's put it in terms of x plus 1 minus in this way, pretty much. Okay, so we'll conjugate that. The reason why I want it in this way is so that now this bottom, this denominator is x plus 1 minus x, and it will just equal to 1. So now this integral, it's just square root of x plus 1 minus x dx. Oh! Now this is just easy. This is just power rule, and this is just a basic u substitution. So now my answer is just 2/3 x plus 1 3/2 minus 2/3 of x to the power of 3/2 plus c. And I'm done. That's all it is. I don't have to do a complicated trig substitution. I could just dive right in here and just, you know, it's just algebra manipulation. Very sneaky though, but whenever I see like some tricky radicals like this, conjugate. ln of x plus 1 over x squared. This looks like I would do integration by parts because I can derive ln x plus 1 and I can integrate 1 over x squared. Alright? I feel like I've done this. Did I do this integral before? I think I'm probably just having deja vu, but I just feel like I did this before. So let's just go ahead. This is x plus 1, but it's negative because alternation. This is negative 1 over x. Okay, so now we have ln of x plus 1 over x plus the integral of 1 over x times x plus 1. Okay, here, super easy. We could just do a zero substitution. Plus x minus x. This is going to cancel out, and then this can cancel out with this. So now this is just going to simplify to 1 over x minus 1 plus x dx. So now the answer is just x plus 1 over x plus ln of x minus ln of 1 plus x. And that's our answer. Oh God, what the hell is this? Don't freak out. Okay, again, you have to be very comfortable with algebra. Very comfortable with algebra to do some speed integration problems like this. So here, they're just exponents. We can split it in two terms, right? And because they're the same exponents, we can absorb them or combine them. And now this is just 2 to the power of x plus 5 to the power of x. Okay, so it's just these simple integrals. And if you remember, this is one of the integrals that you have to memorize. This is ln of 5 plus c. And that is our answer. All right. Again, this let's see. Let's factor that out so that I can get a clear look at this. Oh, okay. This is just a u substitution. That u equal ln of x minus 1. That's just a constant, so just bring that minus 1 in. Okay, and then the du will take care of this. All right, cool. So then this is just du over u. So this is just ln of u, which is ln of x minus 1. Should probably put an absolute value, plus c. And that's it. The integral of square root 1 minus sine of x. What do I do here? We do trig conjugation, right? And what I mean by that is I want to multiply top and bottom by 1 plus sine of x. And what this does is this will make 1, the top will be 1 minus sine square of x. And we know that this is a trig identity, cosine square. So what's going to happen is cosine square is going to be inside square root, and that's going to cancel it out. So we'll end up having cosine of x over 1 plus sine of x dx. And now this is just a basic u substitution. Let u equal 1 plus sine of x. Du is going to take care of cosine of x. Alright. This is just du over square root of u. Right, if you memorize your basic integrals, this is just 2 square root of u, which is 1 plus sine of x. Then don't forget the constant. And you're done. Okay. So, this is very, very strange. What do I do here? So I want to sort of make this, we have an x square, right? I want it where I need something so that we cancel x plus 2 out, right? Well, maybe if we have something like this, right? Then we could definitely cancel it out, right? But then what do I need? So this would equal, this top would be x squared plus 2x. Aha. So I need a 2x. So that's what I'm gonna have to do. So let's do a zero substitution. So I want add 2x, but then I'm gonna have to do minus 2x and then plus 2. Okay. And I end up with x plus 2 here. And x plus 2 here. I purposely cancel it out, and of course we know that this comes into x, so we left off with x. Okay, but what do I do here now? So what now? Now what? I have negative 2x. I don't know what to do with that. Okay, again, ignore the constant. Okay, a constant's a constant. We can just, you know, that's easy to deal with. But we really need to focus on this x here. So negative 2x, again, I need to cancel it out with x plus 2. Okay, so we have negative 2. Maybe we can do negative 2 x plus 2, right? But then this is equal to negative 2x minus 4. So I need minus 4. So I need to do a zero substitution with that. Okay. Negative 2x minus 4 plus 4. And then plus 2. Okay, and this is... Now this can be cancelled out. And this is just... These are just constants. So that's very easy to deal with. So now we have x, and then this is minus 2, right? Because we purposely made it cancelled. So minus 2 plus 6 over x plus 2 dx. Cool. So now this is just x squared over 2 minus 2x plus 6 ln of x plus 2. And you're done. Whoa. That is very weird. So what do I do with this? So But what would you do? So this is actually another very tricky integral to deal with. If you think you could do force substitution, right? Or not force substitution, well, it kind of is force substitution, but it depends on how you use it, right? Let's say you want to let u equal this whole bottom, right? So let u cube root of x minus 1, then we'll end up with this x, and then dx is going to be 3u plus 1 squared du. But then what about here? Well, then this is equal to u plus 1. So we end up with u plus 2, right? You have u here, and then we have times 3, and then u plus 1 squared du. Oh god, we're gonna have this is just nasty, because then you have to square this and then multiply it with this and then divide it with u. So that's just you'd have to be an algebra Olympiad. So let's start small. Let's start small. Okay. Let's go ahead and just let u equal the cube root of x. Then u cubed is equal to x, and we get 3u squared du equal dx. Alright. So then we get 3. If I plug in negative 1, I get negative 1. If I plug in 0, I get 0. Okay. Nothing much. So now we have u plus 1, u minus 1, times 3u squared du. Alright, well that didn't really change much. This doesn't really... How does this make it any easier? You're probably wondering, how on earth does this make it any much easier? Well, so it looks like that because it's, again, this is a very tricky integral, but let me show you. U plus 1, u minus 1, right? If I do zero substitution, minus 1 plus 1, I get 1 minus 1 plus 1, so this would be 2 u minus 1, right? Okay, so then this is just 3, negative 1 to 0, so then this is just 3u squared plus, I'm sorry, I just realized something. That 3 should not even be here, because the 3 is already here. So that 3 shouldn't even be there. Whew, almost messed up. Be very careful. I almost messed up. Ruined everything, almost. Okay, u square, and then 2u squared here, u minus 1. Okay. But now what? Right. So again, I mean, don't let this 2 fool you. This 2 could just be like right here, and then you have like u squared, u minus 1. This is geometric polynomial division. So now we have -1, 0. This is u squared, don't bother. And then 2. Again, you could just do -1 plus 1, right? This is just geometric polynomial division. So we'll get u plus 1 plus 1 over u minus 1 du. Alright, this is much easier, and the reason is because this is just u square, and this u square, it's easy for you to sort of maneuver. So that is why. So let me go ahead and make more room for myself. Okay, so this is 3 times u cubed over 3 plus the 2u, that's u squared, plus 2u plus 2 ln of u minus 1. Alright, so how do we evaluate this? There's a reason why we have absolute value, so that when we plug in 0, it's not, you know, complex. Okay, so then this is so if we plug in 0, everything's 0 here. This is 0 because this is technically 0 minus 1. But then there's absolute value, so ln of 1, that's 0. Okay, so 0 is just 0. Alright, skip. Okay. Let me go ahead and make this -3, because now we're working with the bottom here. Alright, plug in -1. -1 here, that's minus 1/3, plus 1, minus 2, and then -1 here, this will make it, the absolute value will make it 2 ln of 2. Okay, you could technically leave your answer like this, but I'm just gonna go ahead. This is -3, this is 1, this is -1, so that's plus 3, and then minus 6 ln of 2. So now our answer is 4 minus 6 ln of 2. And that is our answer. That was a very tricky integral. A lot to process there. But yeah, another integral to sort of memorize the process. But yeah, again, it just takes a lot of practice and experience. Alright, so what do we do here now? So working with the absolute value, you know, x was 0. So we can split this to -3 to 0. And 0 to 3. Wait a minute. The bounds, -3 to 3. Is this an odd function? Yes, it is. Because the absolute value of x is, this is an even function. This is an even function. And so now this is odd. This whole thing is odd. So by symmetry, this is just equal to 0, and you're done. That's all it is. It's equal to 0. Okay? It's equal to 0. Oh boy, another tricky one. This one, again, it's a very tricky integral, but this one does come up a lot in integration B. So let's kind of learn the process here. So here we see that there's a lot of e to the x. So maybe u equals e to the x, but wait, let's not get there. How about we can bring out the constant here. So e to the x minus 1, but then you'll be left with square root of u with a bunch of other things. So how about we do u equals square root of e to the x minus 1. So let's bring in the square root. I love bringing in the square root whenever we're doing a forced u sub here. So let's go ahead and force a u sub. This will become u squared plus 1 equal e to the x, right? Now you don't actually have to fully solve for x, and the reason why I say that is because look at this, we have an e to the x here. We have an e to the x here. So we can actually go like e to the x dx, and then just go here 2u du, rather than, oh, x is equal to ln of u squared plus 1, we have to derive all that. No, this e to the x can be taken care of. Okay, so let's go ahead and do that. Alright, so then this e to the x gets taken care of. We let u be here, times 2u du, so this would be 2u squared du. And then, but what about e to the x plus 8? So e to the x is u squared plus 1. So now this becomes u squared plus 9. And then our bounds, if we plug in 0, we get 0. Plug in ln of 10, we get 3. Okay. 2 from 0 to 3. Then we got u squared plus 9. You know exactly what to do. Zero substitution. Plus 9 minus 9. So now this is 1 minus 9 u squared plus 9. And so now we have u minus 9 over 3 inverse tangent of u over 3. Okay. And then from 0 to 3. 0, plug in 0, 0 minus inverse tangent of 0, that's all 0. So that's alright. So I like checking things like that. Like, let's check for 0 first. Oh, okay. We're good to go. Right. So, but again, we always evaluate from top to bottom. Let me just erase. Make some room. Alright. So now we go to plug in 3. Of course this simplifies to 3 inverse tangent. So plug in 3, we get 3 minus 3 times inverse tangent of 1, because 3 over 3 is 1. Okay, so it's 3 pi over 4. Okay, so this is 6. So this is 6, 1 minus pi over 4. Pretty much. And then if you could simplify even further, I guess. So this becomes 6 minus 3 pi over 2, I believe? Yeah. So this is 6 minus 3 pi over 2. And that would be my answer. Okay, this looks weird. Let's factor x, because you can, so this is 3 halves. This 1 is like 2 out of 2. So of course we can for sure factor this out. So if we factor x out, right, we get x 1 plus, and then here 3 halves minus 1, that's a half. Oh, would you look at this? Okay, so what we actually have is square root of x of 1 plus, did I do this correctly? I want to make sure I do this correctly. Right, this is what this is, and we factor out the x, right? Okay, so then it comes down to this. Oh, cool, this is a basic u substitution. Let u equal square root of x. The du will take care of this, but don't forget about the 2. So because, you know, the derivative is this, don't forget about the 2. So we get 2 integral du. Let's actually bring in the plus 1. I don't know why I did that, but bring in the constant. Now it's just root u rather than 1 plus u. Cool. So then this is just 4 square root of u, and u is equal to 1 plus square root of x. And that is your answer. Alrighty, this is our last integral, and you will be, you will become officially a speed integrator. Alright, so how do we do this last integral? So this is very weird, right? So this is just a bunch of tangent x's. I don't, I don't like doing force u subs with trig, because then there's just a lot of complications that you have to deal with. Because remember, when you let u equal something, right? When you let u equal something, a force substitution requires you to go like backwards, right? And when you do it with trig, you end up getting inverse trig. So it depends on what you're doing, but in this case, I probably don't want to do force substitution. So, but here's what I can do. We can turn this integral into, in terms of sine of x, cosine of x. And how do I do that? Let's multiply cosine top and bottom. Now, why am I multiplying cosine? It's because tangent x is equal to sine x over cosine x. If I multiply cosine top and bottom, then we simplify it in terms of sine of x, right? So this becomes cosine of x minus sine of x, cosine of x plus sine of x. Alright, what do we do now? What do we do now? Right? This still looks weird, right? But it's actually very easy. This is just a u substitution. Let u equal sine of x plus cosine of x. What do you notice? What do you notice? The derivative is cosine of x minus sine of x. So this is just ln of sine of x plus cosine of x. And you're done. That's all it is, right? Again, integration bee problems, they're full of sneakiness. So it's very important to sort of just experience a lot, practice a lot of integration bee problems, do a lot of integrals like this. Not the tedious textbooks ones. Remember that video. But practice and experience, and then you'll start to notice some reoccurring integrals. And that's where I like to say, it's the best thing to do is memorize the process of these specific reoccurring integrals, so that whenever you come across a reoccurring integral or something similar, you know exactly what to do. Okay? So, yeah, that's it for this whole series. Have fun. And enjoy. Have fun speed integrating. I hope this really inspires a lot of people to get into integration bees. So it's very fun. I don't take this as a math competition. I take it as a sport. So it really means a lot to me. So it's very fun. It's super fun. Yeah, I hope this series helped, and I'm definitely will be making some advanced techniques. Yeah, so stay tuned for that. So thank you guys so much for watching, and I'll see you guys in the next video. See ya.